When your research requires high-performance selective absorption data, choose the new Breakthrough Analyzer from Micromeritics, a fully automated system with flexible gas and vapor mixing for precise characterization of absorbent performance under realistic process conditions. The BTA is a safe and highly optimized device for collecting both transient and equilibrium adsorption data for multi-component systems. It is equipped with patented high-performance blending valves, which minimize dead volume, up to 6 mass flow controllers, and a furnace capable of temperatures up to 1,000 degrees Celsius. The proprietary thermostated environmental chamber provides uniform temperature control. Safety features include automated door lock, shutoffs, and alarms. The flexible, intuitive, and easy-to-use software enables scientists to explore the widest range of conditions and automates the breakthrough experiment from sample activation to data analysis, including the critical ability to perform cyclic experiments. Paired with industry-leading microactive analysis software, the BTA system accurately and reproducibly characterizes absorbance, analyzes data with comprehensive analysis methods, and solves the breakthrough equation for the most demanding samples. Learn more about the Breakthrough Analyzer from Micromeritics at micromeritics.com/BTA.
Hello everyone, and thank you for attending this webinar on breakthrough adsorption. My name is Jeff Kenvin, and I will be the moderator for this webinar. Before we begin, we wanted to cover a few housekeeping items. At the bottom of your screen are multiple engagement tools that you can use. You can expand your slide area or maximize it to full screen by clicking on the arrows in the top right corner. If you have any questions during the webcast, you can submit them through the Q&A. We will try to answer these during the webcast, but if we run out of time, it will be answered later via email. Additional materials are available in the resource list. We encourage you to download any resources or links that you may find useful. Some networks cause slides to advance more slowly than others, so logging off your VPN is recommended. If your slides are behind, pushing F5 on your keyboard will refresh the page. If you experience any problems during the session, you can find answers to some common technical issues located in the Help Engagement tool at the bottom of your screen. An on-demand version of the webcast will be available after today's webcast and will be emailed to you once the session has concluded. I'm pleased to introduce today's speaker, Dr. Julian Hungerford. Dr. Hungerford joined Micromeritics in 2020 as an application scientist. Julian's expertise is in the areas of physisorption, characterization of porous materials, and separations. Julian, it is an honor for me to introduce you today. We are so glad you could be here today to share your insights on breakthrough adsorption, theory and analysis of adsorption in zeolites and metal organic frameworks.
Thank you, Jeff, for that introduction. Today I'm going to be presenting some work on the breakthrough adsorption, theory and analysis of adsorption in zeolites and metal organic frameworks. So to begin my talk, I'm going to begin with an introduction to breakthrough adsorption theory for those that are not familiar with it. And then after that, I'm going to look at some actual results in zeolites and metal organic frameworks, mainly focusing on adsorption of CO2. So to begin with the introduction. So the first question we might ask is, why breakthrough, or why should we care about breakthrough? Before we can talk about that, we need to talk a little bit more about what breakthrough is. So breakthrough is the collection of adsorption data under constant flow by measuring the concentration of gases at the outlet of an adsorption column versus time. This allows you to determine things like adsorption capacity, or for multi-component breakthrough, things like selectivity as well. So why we might want to actually run a breakthrough experiment is we can mimic process conditions and gas concentrations. That's something that's not exactly possible in a static adsorption instrument. Additionally, we can easily collect multi-component adsorption data using a detector like a mass spectrometer, FTIR, or gas chromatography. Breakthrough is also applicable to a variety of different industries. The ones I'll be talking about a little bit about today are highlighted in red, but those include oil and gas, separations, environmental, energy, polymers, membranes, and novel adsorbent materials. So to begin with the first industry that I want to talk about, which is natural gas separations. So natural gas from oil wells and shale deposits typically contains many impurities that must be removed prior to use as a fuel. Additionally, a lot of the toxic species also need to be removed before they can be put into pipes or potentially corrode those pipes. Common impurities include things like nitrogen, carbon dioxide, water, ethane, propane, as well as toxic species such as sulfur dioxide, nitrogen dioxide, and hydrogen sulfide. In particular, the toxic species must be removed per environmental regulations. Luckily for us here in North America, deposits typically contain less sulfur dioxide and hydrogen sulfide compared to any other parts of the world. In particular, the Middle East is known for notoriously high levels of sulfur dioxide and hydrogen sulfide. As we can see, removal of toxic species is extremely important. Additionally, using traditional technologies, it's also quite expensive. Therefore, new materials are being developed to enhance the separation efficiency and allow for cheaper and less energy-intensive processes. The next industry is olefin paraffin separations. Ethylene is a major feedstock for the chemical industry. In 2016, worldwide production of ethylene was number 3 among all chemicals, at over 150 million metric tons produced. The primary use of ethylene is in the production of plastics such as polyethylene. During the production, the separation of ethylene from ethane is critical. Current technologies accomplish this via expensive cryogenic distillation. The two molecules shown at the bottom right, ethane on the left and ethylene on the right, are similar in both size and shape and have similar boiling points. These are some of the most difficult separations via cryogenic distillation and typically require hundreds of columns to achieve the necessary purity for producing plastics such as polyethylene. Therefore, new materials are being researched for adsorption-based separations that can combat some of the expensive parts of cryogenic distillation or completely remove them. They include materials such as metal organic frameworks, polymers, as well as various membranes that are also being investigated for this difficult separation. The last industry I want to talk about is carbon dioxide capture. So global warming has led to increasing concerns regarding rising CO2 levels in the atmosphere. CO2 traps more heat more efficiently than other constituents in air, such as nitrogen, oxygen, and argon. Additionally, with the Paris Climate Agreement, many countries are looking at curbing carbon dioxide emissions to limit the total effects of global warming to less than 2 degrees Celsius. Now, there are a couple different ways that we can go about capturing carbon dioxide. The first is we can capture it directly from point sources, such as natural gas power plants, as well as manufacturing facilities, chemical refineries. The downside to this is there's numerous impurities, much like we already saw on the natural gas capture slide. There are many impurities in natural gas, some of which are toxic species, and separating out all of those species from the CO2 can be difficult. Additionally, your adsorbent may be destroyed by some of those constituents that are found in areas such as natural gas power plants. The good news is, with this method, is that CO2 is at a much higher concentration coming out of these chemical refineries or natural gas plants than it is found in the air. The other option is to capture it directly from the air. The advantage of this method is it doesn't really matter where the CO2 comes from, it's all in the air. The downside, however, is that the concentration of CO2 in the air is only about 420 ppm, although it is rising a couple ppm every year. One advantage of this method is there are much less in the way of actual impurities. However, water does still remain a critical impurity. So we've seen 3 different techniques, all of which are highly applicable to breakthrough and something that a breakthrough analyzer could measure for separation performance. Now to actually look at the different components of a breakthrough system, we have here the micromeridics BTA. So this is our breakthrough system. We can see on the right-hand side we have our gas inlets, up to 6 gas inlets with this instrument. There's also a touchscreen that a user can use to monitor and that the user can user can use to monitor the process. Additionally, it also completely interfaces with the computer for setting up automated analyses. The instrument contains a pneumatic door with a pneumatic door lock for safety, as well as ensuring a highly temperature-controlled environment during the breakthrough process. So gas first enters the breakthrough system and then leads into a system of blending valves where we can blend in all the necessary process gases or adsorptive gases that we're interested in analyzing. From there, it proceeds to the sample column, which we have a sample column that can fit a variety of different sizes, all contained within a furnace, which can operate up to 450 degrees C for standard activation. After that, it then leaves the breakthrough column and the stream is split. One side goes to exhaust and the other side goes to a detector. Additionally, the entire system is temperature controlled via a hot box, which can operate up to 150 degrees Celsius. And this is extremely critical for ensuring that any vapor streams that you use do not condense within the tubes of the breakthrough system. Now looking at detectors, there's two primary options for detectors. The first is a mass spectrometer. So mass spectrometers are generally the preferred detectors for breakthrough adsorption. They have very low detection limits, typically in the parts per billion range, and are BTA interfaces with all major brands. While this will work for the majority of applications, there are some that require other techniques. So the Fourier transform infrared spectrometer, or FTIR, has the ability to distinguish species with the same mass number, which is something that a mass spectrometer is not able to do. Most commonly, you'll use an FTIR if you're looking at something like xylene separation, for example, or any species that have the same mass number. Common brands include MKS as well as Thermo Fisher. Now that we've talked a little bit about our BTA system, next we'd like to go into, okay, how do we actually analyze data for the breakthrough? Well, breakthrough adsorption really contains a three-step process. The first is sample preparation. Next up is activation, and then finally is the actual breakthrough analysis. So samples typically adsorb via physisorption and are easily regenerated before starting a new breakthrough analysis via activation, and then cyclic experiments of activation and breakthrough analysis. First up, let's talk about sample preparation. So prior to analysis, samples should be prepared either via pelletization and sieving, or by dispersing the sample in glass wool or glass beads. This is extremely important to ensure that you have good flow through your column, as you have additional considerations with flow-through systems, including pressure drop and mass transfer limitations. So particles that are too small will lead to pressure drop within the column, and particles that are too large will lead to mass transfer limitations. Now there is no exact one-size-fits-all approach, so depending on your material, it may require different size particles to optimize the pressure drop as well as the mass transfer limitations that are present. Next up, let's talk a little bit more about pressure drop. So as I said before, when particles are too small, gas is not able to flow through the column without disruption. So as we can see here, as we decrease and decrease the size of our particles, what happens is the interstitial void between those particles gets smaller and smaller. As we increase our flow rate, that flow of gas is not able to completely flow through the void space provided by our particles. And that will result in pressure drop, in which at the inlet of the column, the pressure rises, and at the outlet of the column, the pressure drops. When this occurs, particles should be resized to increase that interstitial void space by increasing the size of the particles, or you can instead disperse the particles in either glass beads or glass wool to help separate them further and allow for better flow. Next up, let's talk about mass transfer limitations. So large particles with tortuous pathways will often lead to mass transfer limitations. In general, for microporous materials or any materials where your adsorbate gas is similar in size to the pore window of your adsorbent, equilibration will be slow. What you will see is that your breakthrough curves will be gradual. Smaller particles in general will have less diffusion limitations as there will be less tortuous pathways. This will lead to faster equilibration as well as steeper breakthrough curves. The important thing to note is because you're also highly dependent on your adsorbate molecule versus the size of your pore window of your adsorbent, there are some limitations in how much you can decrease your mass transfer limitations just by decreasing particle size. So let's finish up about let's move into activation next. So activation is used to remove your adsorbed gases or vapors. There's two methods that are most commonly used. The first is vacuum and heat, and the second is gas flow and heat. Both methods are equally viable for the majority of samples. The actual activation conditions that you use in terms of temperature, pressure, and gas flow rates will be highly sample dependent, and it'll depend partly on when your sample desorbs various gases or vapors that it may have picked up during synthesis or adsorbed from the air, as well as the decomposition temperature of your material. The good news is you do have some sort of outlet detector on your breakthrough system, so you can use something like a mass spectrometer to determine when activation is complete, when no more molecules are being desorbed. The last step is breakthrough analysis. So during breakthrough analysis, that's where you actually flow your analysis gases through your sample column, which will eventually be detected by your mass spectrometer or other detector. And breakthrough is complete when the inlet and outlet concentrations are equal or you reach a steady state equilibrium. So after we collect breakthrough data, it's commonly referred to as a breakthrough curve. Essentially what we do is we plot the concentration and how that changes versus time. Shown here is an example breakthrough curve broken down into three sections: complete adsorption, breakthrough, and saturation. During complete adsorption, the adsorbent completely adsorbs the adsorbate gas such that none can be detected at the outlet of the breakthrough column. This is shown in the blue section here, where we cannot detect any of our adsorbate gas in our mass spectrometer because it is being completely adsorbed by our breakthrough column. The next step is actual breakthrough. So this is when you first start detecting your adsorbate gas in your mass spectrometer or other detector. As time proceeds, the concentration that you measure will increase and increase until eventually you reach saturation. At saturation, the adsorbent has reached its maximum capacity and can no longer adsorb the adsorbate gas, allowing it to pass freely through the column. At this point, your breakthrough experiment has completed. So how do we actually analyze our data? And we do that by solving the breakthrough equation shown on the right. The breakthrough equation is an integral from the T dead time, which we'll talk about on the next slide, to the T final, which is when we reach saturation. We then multiply by a normalized concentration, multiply again by a molar flow rate, and then integrate over the time. So before analyzing the data, a dead time will need to be determined. All in all, as we saw before on a breakthrough curve, put simply, the quantity of gas adsorbed by the adsorbent is the area to the left of the breakthrough curve, and if you're using a tracer gas, it would be the right of the tracer gas. So let's talk a little bit about dead time. So the dead time is the time that it takes for the adsorbate gas to reach the detector after starting a breakthrough experiment. So as you can imagine, once you first open those blending valves and start blending your adsorbate gas in with your inert gas stream, it's not immediately going to be detected by your detector. It's going to take some time for that gas to travel through the gas lines, through your sample column, and up the capillary tube of your mass spectrometer or other detector. This time that it takes is the dead time. Prior to analysis, you can determine the dead time by using inert gases and seeing how long they take to register on the mass spectrometer or other detector. In general, once you've loaded and activated a sample, the dead time will not change substantially from run to run. So once you've determined the dead time for a particular sample, you can then proceed to use the same dead time for further experimentation. Additionally, a dead time can be converted to a dead volume based on the volumetric flow rate of the gas. So there's actually a much easier way where you can eliminate this calculation, and that is by using a tracer gas. So what you can do is you can inject a small quantity of an inert gas into your adsorbate gas stream. Typically helium is used for this. And then when that inert gas is detected by your detector, the time between when breakthrough started and the inert gas was detected by your mass spectrometer corresponds to the dead time of the breakthrough column. In other words, your dead time is equal to the time that your tracer gas is detected minus the time that you measured as the start of your experiment, or when those blending valves first initially opened. So looking at what this would look like in terms of the breakthrough curve, we can see that we have essentially two breakthrough curves here. We have our inert gas, which breaks through immediately at the start of our break, when we're first open those blending valves, if say that happened at time equals 30. We also see a very steep breakthrough curve, because if we're using something like helium, which is very small, we don't expect there to be much mass transfer limitations, so we'll get a very steep breakthrough curve. Our adsorbate gas breaks through later as our sample column adsorbs that adsorbate. And then also, it's pretty typical to see some amount of mass transfer limitations, so you might have a little bit less steep curve. The total quantity of gas adsorbed will be the area between these two curves, which is highlighted in red. In summary, breakthrough offers many advantages over static adsorption measurements. It allows you to easily mimic real-world process conditions, easily collect multi-component analysis data, all while under dynamic flow, and then also study flow through a packed column so that you can potentially scale up the analysis that you're running in your breakthrough column to a pilot plant or a full production plant. We also saw how to calculate the adsorbed quantity using the breakthrough equation. While we didn't talk too much about multi-component breakthrough analysis, it uses the same governing equations that we talked about for single component adsorption, and all the same rules apply. Next up, I'd like to move into start looking at some real data and look at breakthrough adsorption in zeolites and metal organic frameworks. So first off, before we begin that, I'd like a brief introduction to zeolites. So zeolites are microporous aluminum silicate materials. They are highly microporous solids, also commonly referred to as molecular sieves. Their structures tend to be very rigid, and they have uniform pore size distributions. Shown here, we have some images of zeolite 13X, which is a very common zeolite used for both CO2 capture as well as air separations. Industrially, zeolites are used for processes such as ion exchange, catalysis, gas separation, and gas storage. Our other materials that we're going to investigate are metal organic frameworks, which are also known as MOFs. MOFs consist of metal nodes connected by organic linkers. They are also nanoporous materials, and they have a great variety in their characteristics and structures, with over 10,000 total MOFs being synthesized and in existence. Essentially, you can think of them almost like Tinker Toys, where you can switch out your metal nodes and your organic linkers and tailor the pore size distribution of your material to better adsorb certain molecules. They also have uniform pore size distributions. Industrially, they have been investigated for uses in catalysis, gas separations, gas sensing, gas storage, as well as drug delivery. So the first experiment I wanted to talk about is carbon dioxide adsorption. So in this experiment, I collected single component CO2 adsorption isotherms on zeolite 13X, molecular Sieve 5A, Mil-53 aluminum, and iron BTC. So materials were initially activated using the appropriate conditions for all the materials as were found in the literature. CO2 breakthrough was conducted using an equal molar flow rate of 10 SCCM nitrogen, 10 SCCM CO2, as well as using a small flow rate of helium as a tracer gas. In general, for breakthrough, you'll always want to flow a small flow rate of an inert gas through your sample to make sure that your mass spectrometer always has gas flowing through it. Otherwise, it'll pull a vacuum potentially on your sample column, or it'll suck in gas from the outside air, which could throw off your measurements. All these measurements were collected at 30 degrees Celsius, and between measurements, we wanted to mildly reactivate the samples without heat, only under nitrogen flow for 2 hours, just to see how easy it was to reactivate these materials. First up, let's look at zeolite 13X for CO2 adsorption. We see fairly consistent CO2 adsorption across multiple cycles. We do see a slight drop off in capacity as we go from run 1 to run 5, likely as a result of not being able to fully reactivate this material without additional heat, as we are keeping our reactivation consistent at 30 degrees C for all these samples. Next up, looking at molecular C5A, we see a much larger decrease in capacity between runs 1 and 2, and then a little bit more consistent between runs 2 and 3. Showing strong first pass CO2 adsorption, however, the material cannot be fully reactivated without heat. Additionally, this material adsorbed the most CO2 of all the materials we measured during this study. Next, we'll move on to the MOFs. The first one, which is Mil-53 aluminum. We can see very consistent CO2 adsorption across multiple cycles, such that we're able to easily reactivate this material without any heat. However, this material did absorb the lowest CO2 across all cycles. And lastly, looking at iron BTC, once again, we see consistent CO2 adsorption across multiple cycles. However, compared to the other materials where we saw very steep breakthrough curves, this one is a little bit more gradual, as we see some amount of mass transfer limitations in this material. However, once again, we see fairly consistent CO2 adsorption across multiple cycles, such that we're able to reactivate this material without heat. Next, I want to talk a little bit about some high-pressure carbon dioxide adsorption in Zeolite 13X. Once again, we collected single-component CO2 adsorption isotherms on Zeolite 13X at total pressures of 1, 2, 3, 5, 7, and 10 bar. We activated the samples for each analysis at 200 degrees Celsius overnight using nitrogen flow, and we did this in between each analysis because, as we saw previously, we were not able to fully reactivate our material unless we exposed it to heat as well. Breakthrough was conducted using the same equal molar flow rate of 10 SCCM nitrogen, 10 SCCM CO2, as well as helium as a trace gas. It is important to note that as we are increasing our pressures, we will also see an increase in our dead time, since we're flowing the same flow rate, the same flow rate of gas, but at higher pressure. So once again, all measurements were collected at 30 degrees Celsius. So shown here are the breakthrough curves on the left, as well as the quantities adsorbed on the right. We see a constantly increasing breakthrough time as we go to higher and higher pressures, which is what we would expect since we're absorbing more and more CO2. We see a first pass capacity of around 3 millimoles per gram, and then by the time we reach 10 bar, we're at about 15 millimoles per gram adsorbed. Then, since we're looking at equilibrium quantity adsorbs for our final adsorption capacity, we can actually translate this to a isotherm, which is shown here, where we can see our increase in our CO2 adsorption, our equilibrium CO2 adsorption, as we increase our pressure. The last study I'd like to talk about is some very recent work that I've been collecting on carbon dioxide direct air capture. So these measurements, we did direct air capture measurements were collected under both dry and humid conditions, targeting 40% relative humidity. Our direct air capture breakthrough measurements were collected by mixing a pure nitrogen stream with a 800 ppm CO2 and nitrogen stream to generate a feed gas containing roughly 400 ppm CO2. Once again, we did also introduce a small helium as a tracer gas to determine the start of the breakthrough measurements. For our support material, we decided to use silica alumina, and we analyzed it both plain as well as loaded with PEI, where PEI is polyethylene amine. PEI is known for being a strong adsorbent for CO2 in the liquid phase, and we tried loading it into our materials by dissolving 4 milliliters of PEI in ethanol, and then we stirred it at 50 degrees C overnight and added our material in as well. So shown here, we have a breakthrough curve for our plain silica alumina, and we can see that our CO2 adsorbed is very small, only about 0.047 millimoles per gram. However, once we loaded it with PEI, we see roughly a 4-fold increase in our CO2 capacity, reaching a capacity of about 0.166 millimoles per gram. Now, looking at it, okay, once we add in water, what happens? Well, we actually see a pretty substantial drop in our capacity. So what we did here is we started by saturating our adsorbent, the silica alumina with PEI, with water by flowing water at 40% relative humidity for 3 hours. And then we started introducing our helium as well as our CO2. And we see roughly a 50% decrease in capacity, only reaching a total quantity of CO2 adsorbed of about 0.082 millimoles per gram. So with that, there's a lot of continued work with this study. Definitely direct air capture is a market that we see expanding for the near future. And we're definitely looking at some ongoing studies in direct air capture, and particularly we're looking at greater PEI loadings in silica alumina, and then we're also going to investigate additional adsorbents. In particular, we're targeting TEPA, or tetraethylene pentaamine, which is shown here around the center. Looking at this as a material that can even better adsorb CO2 than our PEI. We also want to investigate new support materials such as zeolites, moths, as well as activated carbons, and then potentially load these with PEI and TEPA as well. So with that, I'd like to thank you all for attending this webinar on the breakthrough system, the theory and analysis of adsorption in zeolites and metal organic frameworks, and I'd be happy to answer any questions.